zero theorem.
Okay. So, how to find the zeros of a polynomial function when they don't tell you what to start with. So, I'm going to explain this later. I'll come back up because that generic explanation is tough to wrap your head around right from the get-go until you actually see an example. So, here I have a function. And essentially what this is going to build up to is find all of its roots. We don't have a calculator. We don't have a way of factoring this using our traditional methods. So the only way to factor it is going to be via long division, but we don't have anything to start with. They didn't tell us, oh, by the way, 3 is a root, so that would give us something to divide out right away. They give us nothing, okay? So the rational roots theorem gives us a way to find all possible rational zeros. So we're going to come up with a list of possibilities right here, and I'll show you how to come up with it in a second. A list of possibilities. Of that list, not even close to all of them will actually be rational zeros. Probably only 1, 2, maybe 3 of them will be. So we just will then, once we have all of our possibilities, we'll have to just go through and start checking. So we'll have a list of possibilities. Also, if there is a rational zero, it will have to be on our list. Okay, it's not like if it's not on our list, then it's not going to be a rational zero. By the way, what do I mean by rational? Because you can have irrational zeros. This is not going to help us find that. Irrational zeros are ones that are like you'll eventually get from like a quadratic formula, like -2 plus or minus the square root of 15 all over 3. Those are irrational numbers because there's a square root of 15 involved. You also could have imaginary zeros, which this will not tell you because imaginary numbers are not rational numbers. Rational numbers are any numbers that can be written as a fraction. Okay? So, you'll hear me say over and over again, come up with your P's and your Q's. Your P's are all the factors of your constant, and your Q's are all the factors of your leading coefficient. So, any combo of P's over Q's will be your list. Now, just by nature of how multiplication works, factors of positive 4 are 1, 4, and 2, as well as -1, -4, and -2. So we always just throw a plus or minus in front of all this. So those are all your P options. We have 6 of them. 1, 4, and 2, -1, -4, -2. Got it? Over your Q's are all your factors of your leading coefficient, which is just -1. And so the only factor of 1 is 1. You can also put the plus or minus sign on the bottom. It would be a little bit redundant. And so your list is 1 over 1, 4 over 1, 2 over 1, and also -1 over 1, -4 over 1, and -2 over 1. At all the combinations of numerator divided by denominator. So that's, because our denominator is 1, it actually is kind of nice. 1, 4, 2, -1, -4, -2. We have 6 possible rational zeros. So they're not going to tell us anymore, hey, start with 4, because 4 is a root, and they don't give us that insight anymore. You have to know that this theorem tells us from a polynomial what all the possibilities are, and then we just have to start testing. Okay? Now, there's a couple ways to test. If you want to see whether or not 1 is a root, what could you do? What'd you say? Plug it in for x, right? Because if 1 is a root, what will you get? 0. Or if plugging in is a little bit iffy because numbers start to get too big and you don't have a calculator, what would be the second method? Synthetic division, right? So if I was doing synthetic division, I would put a 1 out in front, and I'll do this down below. So this is part B, where we're going to try to search for what are the actual roots. So if I check 1, and then under for my synthetic division, I have -1, 0 to fill the missing x cubed term, 3 and 4, and then I run through this really quickly. Is 1 a root? If I got a remainder of 6, Mitch? No. So 1's out. Then you can move to 4. So like, case in point, 4 to the 4th power starts messing with you a little bit. You might just want to stick with synthetic division. So I try 4. -1, 0, 3, 4. -1, -4, -4, -16, -13. Huge number, it's not going to be 0. What?
Should there be another 0 for the x term?
Oh, you're the best. I could have made a mistake. 0, 4, 2, 2, 6. Okay, that still didn't work. This is still not going to work. Now, now going back to what Olivia said, if we get to 2 and we want to do that in our head, what's 2 to the 4th? 16. So that would be a -16 plus a 3 times 2 squared would be a 3 times 4, which is plus a 12 plus a 4. What does that give us? 0, right? So guess what? 2 is a root. Okay? So now here's what we're going to do. We know 2 is a rational 0. That's one of them of potentially how many? No, I mean, how many zeros total could this thing have? 4. We have 6 possibilities to test from, but we definitely only have 4 zeros, and they might not even all be rational. But I'll tell you what, if you get 1 rational 0, there's a very good chance, well, let me think. If you get 1 rational 0, there have to be at least 2. Right? You guys learned that with imaginary roots last year. Imaginary roots come in pairs of 2. So there's no way something could just have 1 imaginary root. It's either got 2, 0, 4, 6. They come in pairs. And that's because of the quadratic formula, the plus or minus part. So the same will be true for rational zeros, because the plus or minus part. However, something could also be a double root. So 2 might be a double root. So once we find 1, what we're going to do is actually divide it out, and we're going to knock this 4th degree polynomial down to a 3rd degree polynomial, and then moving forward, we'll just check off that 3rd degree polynomial. So we found one of the roots. We're going to divide that out. Oh God, something happened. What did I do wrong? -1, -2, -2, -4, -1. Oh, -2. -4, 0. Good. So I just knocked this down to -x cubed minus 2x squared minus x minus 2. And then I need to keep going, because unless that's factorable. Is that factorable now? By a traditional method? I think it is. It looks groupable. It won't always be. And if it's not, we need to keep testing. But if it is, let's just go ahead and take advantage of that. And then what you'll probably see someone do when they factor is pull a negative out in front and change this to an x squared plus 1. Okay? So this will provide us a root of what? Negative 2. Is that a rational number, an irrational number, or an imaginary number? That's rational, right? So that should have been on our list, and it is. So 2 is a rational 0, negative 2 is a rational 0. And this other factor is going to give us what as our roots? Nope. How did we know that this gave us a root of negative 2? Other than I just know. What do you technically have to do if you're trying to see where this equals 0? Trista? Right, you set them equal to 0 and solve. You're teeing them up. So you subtract 1 from both sides, square root both sides, and so x equals plus or minus I. Sorry, I think that's my phone. Is that the second time it's... Let me just make sure I don't have a sick child. I don't have a sick child. Spam call. You know how that goes. So plus or minus I. Are those rational, irrational, or imaginary? Imaginary. So the only rational zeros we have are 2 and negative 2. So of our list of possibilities, we had 6 possibilities, 2 of which panned out. Okay? The other 2 roots, because we're supposed to have 4, because degree of 4, we kind of already talked about that. Find all the roots, we just did that. 2, negative 2, plus or minus I. Okie doke. Any questions? So now let me go back up to this more confusing definition than it needs to be, but that's how definitions are in math, because we have to write them generically. So let f of x essentially be a polynomial. Your p's are any factors of b, the constant, and your q's are any factors of a, your leading coefficient. So then all the possible rational zeros are given by any valid integer combination of p over q. We say integer combination, and I think that's a little redundant. Factors have to be integers, right? We usually, you don't say like, you don't break down factors and use decimals to do it. Like for 7, right? You would never say that 3.5 and 2 are factors of 7. So factors by nature are integers, so I don't really know why they added that, but we follow? Okay. Oh boy. Solve. So first, find your rational zeros, possibilities, right? So your p's over q's. We're going to get 1, 24, 2, 12, 3, 8, 4, and 6. Well, that's a lot. Not to mention the plus or minuses that have to go in front. Over, our q is just 1, so thank the Lord for that. So we have, how many possibilities? 16. My suggestion, start with the smaller numbers first. Keep your fingers crossed. So I'm going to start with 1. What's 1 to the 4th? Minus 6 times 1, minus 8 times 1, plus 24. Does that equal 0? No. So that's out. Then negative 1 will give us 1 minus 6 plus 8 plus 24. Does that give you 0? Darn it. Okay, I'm going to cross out my 1 because it didn't work. 2. What's 2 to the 4th? 16. Minus 2 squared is 4 times 6 is 24. Minus 8 times 2 will be minus a 16 plus a 24. Does that equal 0? Good. So 2 works. So let's synthetically divide that out, so that'll shrink up our 4th degree polynomial. 1, 0, negative 6, negative 8, 24. We good with that? Do your synthetic. We already know we should get 0. So now our tester is x cubed plus 2x squared minus 2x minus 12. So we pretty much from this point forward can ignore the original. Now, we just found that 2 was a factor. Is this factorable by hand? Okay, so we have to keep going with our tests. So we just left off testing 2. When we start testing again, we're going to start by testing 2 again, because 2 could be a double root. Does that make sense? So if you think, oh, 2 was a root, and you just move on and now check negative 2, you might miss that it's actually a double root. Does this make sense? So if I've just found 2, I'm going to pick up with 2 again. What's 2 cubed? 2 times 2 squared is another 8. Minus 2 times 2 is minus 4. Minus 12. Does that equal 0? Okay, so it actually was a double root. And you might want to write that over here when you're listing your roots. But now I'm going to synthetically divide out the 2. Just to see now that my cubic polynomial is going to get knocked down to a quadratic. And once you're down to a quadratic, you can do the rest by hand. So this is x squared plus 4x plus 6. Is that factorable? No. But can I still solve it to find the other roots? Yes. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative 4 plus or minus the square root of, that's going to be a 16 minus a 24. Negative 8. Reduce. Keep reducing. And there are my other 2 roots. So I have my 4 sort of solutions. 3 distinct solutions, right? 3 different ones, but all 4 are accounted for, because that's a double, so that counts as 2, 3, 4. So my solutions, right there. Try the next one on your own. Don't do the last one because I'm going to change that answer. Or I'm going to change that problem. right? Which will be positive 1, positive 3, negative 1, negative 3. Excellent. Okay? And then what worked? Bailey. Okay, so if negative 3 worked, I'll check it for her. I have to do this anyway to reduce the cubic down to a quadratic. 1, 7, 11, negative 3. Okay, it did work. Oh, that's 4. Okay, so now my cubic becomes a quadratic. That's x squared plus 4x minus 1. So now when she picks up testing again, so how many people tested 1 first? It didn't work, right? If 1 didn't work in the original, it's definitely not going to work later on either. So once something doesn't work, you never have to check it again. Okay? And then if you check negative 1, that didn't work. And then you checked negative, or 3, did you check 3 next? That didn't work. Then you checked negative 3. Finally, it worked. If you were to continue with the checking process, you would recheck negative 3 in now the quadratic. But because this is a quadratic, once you get a quadratic, forget this whole process. Move forward with just factoring a quadratic the way you know how, or the quadratic formula. So we have 3 zeros. 1 is rational, and the other 2 are irrational, which is why the other 2 were not on our list. Good? Now, I can't remember why I put that one there, but I immediately noticed I never had one yet with a coefficient out in front, so I want to do this one. So copy that one down. I'm going to just set that equal to 0. It's not factorable, so obviously we have to use our P over Q process, which will be plus or minus 1 over, now our coefficients of Q, we actually have 1 and 2, or our factors of Q. So on this one, 1 over 1 is 1, 1 over 2 is 1/2, and then you also have negative 1 and negative 1/2. So this is a little bit annoying because you do have to check a fraction. Did you do synthetics last night with fractions? Okay, so again, plugging in a fraction might be a little tricky, but let's say I started with checking 1/2 via synthetic. Okay, same process, bring down your 2, 1/2 times 2 is 1, 1 plus 1 is 2, 1/2 times 2 is 1, negative 3 plus 1 is negative 2, 1/2 times negative 2 is negative 1, 0, look at that. 1/2 works. So fractions are still rational possibilities when they come up, and you have to be comfortable just checking a fraction. So now I do know that my cubic is now down to a quadratic. I can actually divide everything here by 2. This is not factorable, so my solutions are going to be 1/2, and then whatever 2 irrational answers, this, or maybe imaginary, I'm not sure, but this quadratic formula will produce. Okie doke. So, homework, there at the bottom. Quiz tomorrow. I do not believe the rational root stuff will be on there. Synthetic will be, but not the rational roots. Okay? So, obviously do your homework, but don't get bent out of shape on this in regards to preparing for